Yeah.
Alexandre here, Choquette, and additional members from the IBM team coming here today. They will tell us about IBM Quantum, the tools that are available to us. We record this seminar, so from our experience, then many people check it out. This is reading week, so probably fewer students are around. They are studying. But yeah, thanks a lot. And again, I'm sure this is a great use for our students. So, please.
Yeah. Yes. Yeah. Awesome. Yeah. Thanks, Evira. Just to make sure if do people on Zoom hear me? Yeah. Just to make sure it's the recording's working well.
Yep.
Yes.
Yeah. Okay. Perfect. Awesome. Yeah. So yeah, happy to be here. My name is Alexandre, and so so my background is in quantum computing from University of Sherbrooke. And then during which I worked a little bit with IBM Quantum in Zurich, was mainly working on variational quantum algorithms back in 2017, 2018, when they were still very young and nobody quite knew what to do with these quantum systems. I remember at the time IBM had just put a 5-qubit system on the cloud, and we thought it was amazing. We could drag and drop our little gates and kind of send our programs and basically collect noise. Today the landscape has changed a little bit. Now we have these massive systems with an increasing qubit count. So I'll talk all about that. So coming from seeing the fields starting from the ground up, I think I can speak for everyone. If you ask people in 2017 how long it would take to have multiple 100+ qubit systems available kind of worldwide on the cloud, I think it would be the estimates would have been further than where we are today. So we're kind of happy with the development. So I'm going to talk about that and a little bit where we're going from then. And also, so the reason we are here with some IBM colleagues here is because the University of Toronto is now part of the IBM Quantum Network. So the IBM Quantum Network is a very large network of close to 300 institutions worldwide, mainly academics, that in part have access to our IBM Quantum systems. So and some of them we're collaborating with to do some algorithm development and cool research using IBM systems. And so PINC now has access, University of Toronto, through a nonprofit organization in Canada called PINC, has access to the quantum computers. We have one in Quebec in Canada. So so we're happy to see what you're going to end up doing. All right. So the talk is called Tools for the Utility Scale and Beyond. So we will, I'll try to define what that means. So let's take a little step back and, and try to understand, okay, why do we use classical computers in general? Before wondering what can we do with the quantum computer, let's take a step back. And so let's take a example problem. So if probably every student that did a little bit of a linear algebra was asked at some point to compute the determinant of a 2x2 matrix. Who has done that by hand? That's a 2x2 matrix. Pretty easy, right? There's like a simple formula. You can probably do it in your head. Then a 3x3 matrix. Who has done that by hand? Okay, probably it took you, I don't know, 10, 15, half an hour, depending on the matrix. Then 4x4 starts to get challenging. It really requires you to pause and think about it. But 5x5, I've never done a 5x5 determinant calculation by hand. But for the sake of the exercise, we ask JSTA. So Jays is our big boss at IBM Quantum, and we asked him back then to compute the determinant of that matrix, and his competitor was a NumPy that the determinant. And so let's see who won. All right, so the results for JSTA, we got like minus 624,372, as you would have guessed, right? And NumPy got a slightly different answer, so minus 623,999, but plus some floating point error. So right now, which one do you trust? Slightly different numbers. I think we're kind of tempted to trust the computer here more than the human being. And that's one thing. So the accuracy of the computer. And then the other aspect is how long it took. So for by hand calculation was 1 hour and 20 minutes, which is kind of good performance here. And then NumPy took 2.17 microsecond, which is about 2 billion times faster. Okay, so what did we learn here? Okay, and so we learned that, okay, for this small system, for this small problem, we tend to trust it. So why not trust it as we scale up? If we have an algorithm that we know, scales up, we're tempted to also trust the answer a computer is giving you at large scales, even if there's no way for you to verify that the answer that the computer is giving you by hand calculation. And so kind of the reason why you like to trust classical computers is many different reasons, including like accuracy, so you can get good answer, speed, because you don't want to spend hours of your time just doing things by hand, scalability, because you can try bigger and bigger problems, and also versatility. I don't need to convince you that computers are useful for basically everything we do in our life and in every sector. So that's why we like computers. Okay. So we've learned to trust that classical computers can be accurate at scale. Now the question, if we translate that to quantum, is can we trust that quantum computers execute quantum circuits accurately? So quantum circuits are the programs that quantum computers deal with. And so as of now, our answer is yes, and we're well on that path. So about 1.5 years ago, we published these experimental results in Nature, where we basically showed that the quantum computers that we have available today on the cloud, they can produce accurate expectation values. That's the answer of a quantum program on scales that are up to 127 qubits with close to 3,000 gates in regimes that are outside of brute force classical computation. So for problems that we don't know the exact answer to, we are forced to, if we want to solve the problem classically, we're forced to use classical approximate methods like tensor network. And so, and the quantum computer was able to, to produce good results. So maybe a good way to look at this problem is, say I'm giving you 10 different black boxes. Okay, so they're computational black boxes, and for each of them, I'm gonna plot the results of some expectation value or whatever you want to measure as a function of some tuning parameter here. And so for each of the black boxes, it gives you a cloud of data like that. And but it's hard to say which one is the right one. And then you can draw some like certainty area. And then turns out that one of these black boxes say is in an IBM Quantum computer, and all the other ones are tensor network methods. So if you just look at this cloud of data there, it's basically impossible to say which one is right, which one is wrong. You can because we don't know the exact answer to the problem, but we can we have a fairly good idea that the answer is somewhere in that cloud of data. And so for that specific paper, what was the problem that we tackled? So it was basically a kind of a poor trotterized evolution of the transverse field Ising model. So it's a model that has a quantum ground state depending on the value of the X term here, and is something we can kind of easily map onto the quantum hardware, providing the right topology. And so the trotterized evolution is basically you take the exponentiation of that Hamiltonian, which in this case translate to a bunch of ZZ gates, and the X gates are single qubit Rx rotations. And so the circuit might look like that for one step of the trotterization. So we get the Rx and then the ZZ gates. And then because the goal was to show what our hardware can do, so that's a map of an IBM quantum computer here. You can see all the qubits, and we basically chose a topology for the Ising model that fits the hardware, so that we didn't have to commute qubits around. So the connections of the qubits are the connections in the problem, and so every layer of ZZ gates would just map to the nearest neighbor 2-qubit gates. And so you can implement one layer of every trotter step in kind of this 3-column of ZZ gates that represent the kind of the three colors here on the graph. Okay, so that's the problem. And then so exactly like we did for the matrix determinant case, we first need to gain trust in in what the quantum computer is giving you. So the first step that we did for that problem is to first start by computing circuits that we know the exact answer to. So it's just because they are at a scale where we can still use exact classical methods. And so that gives us confidence that the quantum computer is producing good, well, accurate results. So what you get here is, so you can trace the exact line. That's the kind of dark gray line. And then if you run the quantum computer, what you get is these green circles, which like qualitatively match what the exact answer should be, but not exactly quantitatively. And so what we did, and that's because of noise. So with quantum computers today, they still have a lot of errors, lots of noise. So we need to mitigate that. And so we have a lot of like tips and tricks to basically average out the noise. And when we perform these, so that costs more circuits, but when we perform these, we can recover relatively accurate data. And then for the sake of comparing with classical methods, we partnered with some collaborators at UC Berkeley, which at the time produce very accurate, very powerful tensor network methods. And these are these other lines here. So we can see that at lower Rx angles, which matches the kind of low entanglement in the system, these tensor network methods are typically very good at low entanglement, so that's why you get good agreement. But as the entanglement grows, we can see that these methods are starting to crash. Okay, I would say, also importantly, what we are measuring here are so either here kind of the overall magnetization of the Ising field, or here kind of a long like polystring measurement. Why that one in particular? There's no real reason. The important thing is that this type of measurement or this type of expectation value resembles a lot what you would need to measure if you were doing quantum chemistry problem. So if you're doing quantum chemistry, you need to sample different terms of your Hamiltonian, and they would be measurements that look like this. So even if that one is not particularly useful, it looks like a problem that is useful. And so now what we did is we scale it up to 68 qubit and eventually 127 qubit. And that's in a regime where we cannot get the exact classical answer. And so all we are left is the quantum computer, the error mitigation methods, and the approximate tensor network methods. And so here, where we measure again the quantum computer, we get this data and we compare, and then we have kind of no way to know if that's the right answer or not, except for the endpoints. So it turns out that if you computed the math for these angles, the circuit become what we call Clifford circuits, meaning that they are easy to simulate classically. So at the endpoints of the plots, we know exactly what the answer should be. And somewhere in the middle, this is where we don't know yet. So for example, we can see that this tensor method is crashing as we increase entanglement. So that's for the accuracy. Now remember, there's also a speed component. Turns out that for this experiment, which is already a year and a half old, the classical method was taking a lot longer, so like 2 to 3 times longer than the quantum data. And also importantly, for out of the say 9.5 hours that every quantum data point required, there was only 5 minutes that was actually spent on the quantum computer, meaning that basically all of that 9.5 hours minus this 5 minutes was spent doing classical compute, so pre-processing and post-processing to make the quantum computing happen. And so that made us realize that the runtime right now, well, at the time was bottlenecked by classical software, and we've like drastically improved that since then. Any questions?
Did you get it?
Yes.
Pre-processing, is that like circuit optimization or what kind of?
Yeah, exactly. So there's so first there's mapping your problem to the hardware, which in this case was trivial because we chose a problem that mapped to the hardware. And in principle, if you would have to see which qubits are the best to map your problem onto, then it's transpiling your circuit. because when you write your circuit with pen and paper, it's not exactly what's going to be happening there, and then transforming your circuit into pulses and then sending it to the hardware. And then post-processing is like a lot of error mitigation methods. I think you had.
How long does this pre and post processing, how well does it scale as you get bigger and bigger problems?
So you mean for the error mitigation specifically, or?
Well, it's not going to be much of a quantum computer. We've got an exponential amount of pre-processing to do.
Right. Yeah. So if all you care is just to sample like a one quantum circuit, then this scales very well. The error mitigation method is an exponential process, but the curve is smoother than the exponential cost of simulating the same circuit classically, meaning that there's our thesis is that there's still an advantage in using this method. And importantly, you get an exponentially better, smoother curve as you increase the quality of the hardware. So when the error rate reduces on the hardware, then your costs of error mitigation reduces drastically. So that's encouraging. You had a question.
First, do you get indeed the endpoints to be according to the exact prediction? You said the endpoints in those graphs are no. So did you get them properly in the quantum computation?
Yes, so we know that like we need to be at 1 here, for example.
And the other question, so usually when we do classical, let's say the tensor network, there is a sense of convergence. We can see that as we increase certain parameter, we see convergence to fix the point. Is there also a such measure when you do mitigation, where you can see that indeed you converge to something, or is it?
So I think it depends on the problem, right? If you're trying to do like a ground state problem, then you might have some iterative method, and you're gonna see where it converges. In that case, I believe we just started with an initial state, which I think was a plus state, and then we just time evolved it. So we don't know exactly where it's going, right? It's just kind of being time evolved. So it's harder to define a convergence. Yes.
So I have two questions. One is, what was the time of evolution? How long did you evolve the circuit for?
Yeah.
What was the time that you?
Yeah. So for these circuits, so okay, I don't have like the full circuits, but I think it was 20 time steps, 20 trotter steps at the biggest.
Like I mean the total time of evolution, like e power minus x, right? So the time you took from that.
Well, we'll have to look at the parameters, but it was, so, we trotterize the time evolution in like time steps, and the more time steps you put, the longer your circuits become, and the harder it is to execute. And at the maximum, we had 127 qubits by 20 time steps, which mapped to 60 qubit, 2-qubit gate there. Right? But you have to look at like what was the total time divided by 20.
The main reason for asking was, the error grows if you let the time evolve. Right, like if the time step is larger, than the error is larger. But for classical methods, I don't think time step is really important.
Yeah, but here you can basically choose whatever angle you have in front of every trotter step. So you have control over the total time.
But won't that affect the errors on the quantum computer?
Yeah.
Like if I evolve the system for a long time, then error I'll accumulate will be much larger than smaller time. And another question was, so in this one, you chose the system to have the same kind of structure as your actual circuit, like in only neighboring gates. How will the time taken change if you have all kinds of interactions and not restricted interactions to be that of what the geometry of the qubit is?
Yeah, so like if you're trying to solve, say, a square lattice or another.
Yeah.
So there's still a way to map it, but it's going to cost you in gate depth, because you're going to need to shuttle qubits around to create the interaction that you need, and then shuttle them back. So it just adds a lot of like swap gates everywhere. So as a kind of a proof of principle, for us, it's better to swap it directly to the hardware. It's actually a good way to approach your problems as well. Like, what problems can you solve if you're like mapping it directly to the hardware? Yes.
Do you have the results for other examples, like larger questions or easier questions, and how long does it take for classical computers?
For like larger problems,
Yeah, small. questions, so we know how pre-processing more computation steps cost?
Yes. So for that paper, these were the kind of the biggest circuits or biggest system that we use. So we do have an idea of like how much it costed for the pre and the post processing, and also a lot of this was like tailor-made just for that experiment. And now we've kind of streamlined a lot of that into Qiskit. So we've taken a lot of the methods that we use and optimized them, and now they're part of Qiskit. So you can even like test it yourself and have an idea of like how long it's taking. Awesome. And so, yeah, so since we published that paper, kind of expectedly the classical tensor network community and wanted to reproduce the results, and that's exactly what I think we need to do as a community. And so we've seen this this slew of paper that these tensor network methods that basically reproduce the 127 qubit circuits, or like the largest circuits that we had. But still, they don't, as I showed in the previous plot, they don't all agree, right? There's still kind of this 20% variation between the methods, and kind of in the middle of it, there's the quantum data. So one thing we could argue is that maybe we can start to, so we start to flip the script, right? We can start using quantum computers to verify the outcome of tensor network method, or kind of vice versa. So kind of both methods are becoming, useful to approach different problems. Yeah, so just for fun, that was the largest circuit that we ran. So that's 127 qubits by 62 qubit gate depth. So that's 20 time steps of the Trotter evolution. And as a comparison, I was saying in the beginning, in 2017, kind of the biggest one that you can do is 4 qubits and 2 qubit gate depth. So which maps to like this tiny block here. So things have changed a lot in the last few years. So yeah, so looking at this circuit, you'd be like, okay, how is it possible? If you look, you can look on the IBM Quantum website and look at our gate errors. Okay, and if you see that there are about 0.5% for every gate, and we have close to 3,000 gates, then the probability of success should be something like 10 to the minus 7. But still, we can get a decent signal out of these large circuits. And so the key here really is the error mitigation protocols that we're using. So if you have one thing to remember about this paper, it's not necessarily about solving the Ising model, but it's really about demonstrating how powerful these error mitigation methods can be to get an accurate signal. So that really is the takeaway. And just at a very high level, the way we did the error mitigation in that paper is that we first need to learn the noise. And for that, we're using these Pauli-Lindblad sparse models to learn the noise. There's a reference here if you're interested. But basically, it's looking at every entangling gate. It can be applied as a perfect gate plus a kind of a noise channel. And so we learned what this noise is, and then from them there's like two approaches. Once you know what the noise is, you can either use that information to cancel the noise. So that's what we call PEC, so probabilistic error cancellation. But that is quite costly. It was too costly for us to implement in that paper. Instead, what we did is we amplified the noise. So once we know what the noise is, we can basically add gates to it controllably, so that we basically amplify the noise in the system. And then we can kind of trace what the noise is, what the results are as a function of this noise gain factor, and basically extrapolate back to the zero noise limit. So you can either extrapolate linearly, or in this case, we did exponentially, and there are reasons for both. And that's what gives us the error mitigated value at the end of the circuit. So kind of very neat stuff. And I believe all of that is coming to Qiskit eventually as well, like the PEA protocols. All right. And so since we published that paper, I think it inspired a lot of the community to also try to see what they could do with these large circuits, that use roughly 100 qubits and with many gates. And so we've seen kind of this slew of paper coming out from the community. Some of them were by IBM, some in partnership with IBM, but some others that we did not even know that people were publishing, and they just came out on the archive. And so now we're seeing all of these, what we call utility scale demonstration across many fields of science. And there's even like a little second page here. So it would be good to have a few UFT demonstration here next year when we come back. All right. So, okay, kind of the main message here is that as we see more and more of these utility scale demonstration, and that we see that people are getting value out of running these large circuits, that's kind of how we commonly gain trust into the quantum computers, right? It's not isolated results. It's kind of a community that see value in using these systems. So another kind of paradigm that we're bringing to the table, or another narrative that we're bringing, is the idea of a quantum-centric supercomputing. So here we're taking just a step back from like the specific quantum circuit demonstration. And we're trying to think what is the architecture, like the supercomputing architecture of the future look like. And a lot of time people like to compare quantum versus classical. We think that eventually it's going to be quantum and classical together inside the same supercomputer. And that's what we refer to as quantum-centric supercomputers. And so you might expect like having a big data center and some that will have like CPU racks of CPUs, GPUs, and any flavor of processing units that you want. And then that will be co-located with some QPUs, which themselves have some quantum component, but also need some classical infrastructure to control the gates and do the pre and the post processing. And that is much faster if it's co-located with the quantum computer. And so that's where we're going. And to kind of illustrate that, we wanted to do a proof of concept demonstration on quantum chemistry in that case of how this type of architecture could be useful to solve important problems. And so what we did here, so that was a collaboration that we did with RIKEN in Japan. And I won't necessarily go to all of that, but basically what we did is we coupled a Heron chip, so that's the quantum computer, with the Fugaku, which is a very large HPC infrastructure that they have. And we have this protocol to basically sample a lot of data out of the quantum computer. And here you want to frame the problem in a way that the transfer of data between the quantum and the classical is the bottleneck. So like, for example, if you think of a Varshal algorithm, like a VQE, for example, there's very little data that goes from the quantum to the classical, right? You're just measuring an energy, and then you're sending this one metric, the energy, to the classical computer, which optimizes and then just sends a small array of new parameters. That's not what we did here. So what we did here is we basically sampled all the shots from the quantum computer. We did not even care about error mitigating the data. We're just collecting all the shots, and then we have this configuration recovery protocol on the other side. So we're basically looking at all the shots. Some of them are noisy, some of them are not, and we have a protocol to basically flip a few bits in the shots that we had, and then take this Hamiltonian and kind of project it into like smaller subspaces that we then diagonalize classically and kind of in parallel using the HPC, and then we were able to kind of recover the energy of the system. And so we tested that method on for that work on 3 systems. So first, it was the N2 molecule, which is a good benchmark molecule for classical quantum chemistry methods. And then we tested these 2 other molecules, so the Fe2S2 and Fe4S4, where we push it all the way to 77 qubits. And the interesting thing is that if you try to estimate what would be the cost of measuring the energy for these molecules using different approaches, even with like fault tolerant, just a purely fault tolerant like pure quantum algorithm, in here we use a surface code for discrimination. If you want to measure 6.7 million poly operators on 72 qubits, then that would take 13 days runtime. If you wanted to use the same, if you wanted to use VQE at that rate of measurement per second, that would take like 3 million years to get the energy. So that doesn't scale well. And then with this approaches, we could do it in like only 2 hours. So that really goes to show that having HPC and quantum can help speed things up. So yeah, don't need to dive into the details, but basically we computed the bond breaking or the dissociation curve for the N2 molecule, and we found that the best classical method for that problem was the HCI, and it compared quite well. And then for the Fe2S2, we're able to get results that and sometimes match the MRG methods, which is a very powerful method for a classical method. And then we're able to get some signal for the Fe4S4 at 77 qubits. So that's showing that this method scales well, and you can still get a relevant signal at that scale. All right, so I'm going to switch gear here. So is there any question before?
When you compare the time for each of the methods, like for repeat, was the accuracy the same, the target accuracy?
I don't know exactly. I would assume. But yeah, do you guys know? Yeah, I don't think there was a statement about accuracy, but I think that's just the time it would take to to measure all these terms.
Okay.
But you're right. I would say, like, for the VQE, if it's pre-fault tolerant, you would need some error mitigation protocol. So that probably went into the estimation of the time it costs. And yeah, to get a right estimate, you probably need a level of accuracy that you wish. I would think maybe chemical accuracy would be a good place to go. Yes.
For the error amplification part, you said you add some gates that'll give you the same noise property.
Yeah.
What specifically, like, gates would you add? Is it just the same circuits and then it's inverse, or?
Yeah. So remember I told you we learned the noise, and in the noise model, it's basically like we map every gate to a perfect gate and then a noisy gate. Then we learn what this noisy gate is, so we can just reapply that noisy gate, and that just amplifies the noise. And then we can do it to, say you have 102 qubit gate, that you can do it to only one gate and just adds a little bit of noise. We can do it to 2 gates and add a little bit more noise. So that's how we can control this noise gain factor.
But this noise gate is not unitary, right?
No, it is, because I think we're doing poly twirling, so it transforms. Maybe Nick, better.
It's probabilistic.
Yeah.
So you're running a number of circuits and then you're only injecting pulses.
Yeah.
So 2 questions. First of all, you described before doing the error mitigation to characterize the sources of error. Such like that. What does that involve? I mean, is it full process tomography? And that's going to be very slow, especially as you scale up. What do you do? So it can't be that.
No.
What is it? What are the shortcuts you take?
Yeah, so that's a sparse Pauli Lindblad model. So we don't so it's not an exponential. I don't know exactly the cost of that. Maybe Nick, you would know better.
Yeah. So if you look at the full we're looking at poly transfer maps as characterized into error. So that's 4 to the n, which is bad. So what we do is we twirl over the error channels and do a technique called poly twirling. So we get a diagonal matrix.
Yeah.
And we relearn that. And that's the error model.
Okay. Then I'll follow up on this later.
That's good. All right. Now the fun part. Yeah, so I think last year we announced our new kind of workhorse chips, and these are the Herons. So previously we used to have like the Eagle chips, and we did a lot of changes for the Heron chip. One of them is that we changed the way we're doing the 2-qubit gate, like the physical processes to do the 2-qubit gate. So we went from a cross resonance gate with fixed frequency qubits to a tunable coupler. So now so the qubits are still fixed frequency, but between every qubit we have kind of another tunable coupler, and that's what we're using to drive the 2-qubit interaction. And programmatically, how it affects the users is that now the 2-qubit gate, it goes from a C0 to a CZ. That's to keep in mind if you're programming the different devices. And so the Heron chips, they kind of they fit well into this our version of the Moore's law. So that if you look at all the devices that we've put on the cloud as a function of the release date, we see that the error rate, so that's the n-thing leg, so the 2-qubit error rate is kind of going down in this somewhat linear fashion in the log plot. And you see that all the Aeron, and we're already at Aeron R2, so the second revision of the chip, they're really neat systems. And so that fits very well into the development roadmap from IBM. So I'm sure you've probably seen that slide somewhere. So if not, then know that IBM, I think since 2020, we've always put our development roadmap available publicly, so that what we accomplish and what we're working towards. And we revised the roadmap last year to basically speed things up, right? And so one thing that we changed is, instead of like scaling up the number of qubits per chip, now we're trying to scale up the quality of the chips a lot more. So the kind of the number that's increasing here in parentheses, that's the number of 2-qubit gate that you can run in your circuit. So right now we have the Heron chips, so we can take that at the end of the year. And then we're working on the Flamingo chips, where we are going to connect different Heron chips together to create a kind of a bigger cluster. One notable thing about this roadmap is that if you look in 2029, the number of operations that you can do will jump from 15K to 100 million. And that's because we are going to start implementing error correction protocols in our devices. So that will go from error mitigation, which is like collective measurement of a lot of circuit to average out the noise, to active error correction, where we can correct the errors on the fly as the program evolves. So that will increase by a lot the number of operations they will be able to do. And we're going to have 200 logical qubits by 2029.
Is that the logical 100 million? Is that the total number of operations you're doing?
Yes.
The logical.
That's a good question.
Because you're going to have a bunch of operations to the error correction.
Yes. So I believe this is the number of gates you will be able to program yourself.
Physical gates.
And then we will let Cascade runtime to do the error correction on top of that. Yeah. And then by sometime in the 2030s, we can jump up to a billion gates per roadmap. Also, notable things to be on the lookout for is the error correction, the decoder demonstration in 2026. That's on the roadmap here. Oh, and I should mention, we have two roadmaps now. We have the development roadmap at the top. So that's what is going to be kind of released to the public and available to the IBM Quantum network. And then the innovation roadmap is basically the tech that we need to develop to enable the development roadmap. So that's why it's typically like a year or two in advance, and eventually it makes its way up to the roadmap. So like, for example, Flamingo, all the modular connection, we already have demonstrations internally, and they will make it up to sometime in 2025 to the development roadmap. Any question on the roadmap?
Sorry to.
Don't apologize, it's great.
I seem to remember, and I'm not pretend to be an expert. The superconducting circuits, you connect them all via a microwave cavity, microwave wave. How much interconnect between different qubits are you going to be able to do?
Yeah, so I'll talk a little bit about that. Right now we don't see like strong reasons for us to steer away from the heavy X pattern. I don't think it would be such a big deal to switch if there is a very good,
Sorry, you're getting beyond heavy X.
Yeah, so that's the pattern that I should say for the qubit connectivity or the topology of the qubits. So some qubits are connected to two others or have two neighbors, some have three neighbors.
I see.
So it's kind of a honeycomb lattice with extra qubit on
So
some
you're
edges.
still gonna have essentially nearest neighbor interaction.
Yes, and but I'll get to the question later. But in order to implement the error correction code, we need extra degree of connectivity, which we already have some experimental results. So yeah, so that's the heavy X pattern. So another neat thing that's that has come in the R2 is a two-level system mitigation protocol. So if you know a little bit about superconducting qubits, you will know that there are spurious two-level systems that live in the qubit substrate, and these are basically qubits that are there but that you don't want to be there, and they unwantedly couple to your qubits that you're trying to control, and so you have a lot of leakage into these two-level systems. And so we have found a way to basically tune away the two-level systems that we have on the chip, and that drastically increases the coherence times of the qubits. So this we're quite happy with, and it's already enabled in the Aeron R2. I think we have the IBM Fez, and it's online today. Yeah, and if you kind of look at how the errors have decreased over the years, since we released IBM Cusco, we already have like a 16-fold improvement in the effective errors, with some of the best entangling rates being very low, in the 10 to the -4. So quality is good, but we also need to, we talked a lot about pre and post processing, but so we need our chips to be really fast, and that's a key advantage of superconducting qubits. But we also need the classical infrastructure, kind of the runtime infrastructure, to be very, very fast. And so we have developed this metric to benchmark how fast we are, and it's called the CLOP. So that's like circuit layer operation per second, and so I mean, we are projected to be over 100K of CLOPs by the end of the year. So that is something that we need to do if we're building a fleet and that have many users sending lots of jobs at the same time. We cannot afford them to be slow. So kind of in summary, every time we put a new system on the cloud, we always say that the performance, it cannot be only the number of qubits, it cannot be only the coherence time, or it cannot only be the speed. It needs to be a combination of all of them. So that's why if you look at the different cards for the computers that we have on the cloud, you will see these kind of three metrics being reported here. And importantly, when we measure the quality, so it's some measure of the 2-qubit error rate that we call the EPLG. So that's the error per layer gate. So we basically build these chains of 100 qubit and compute what the 2-qubit error is for these 100-qubit chain. So it gives you a good metric on, if you're running large circuits, what sort of error you can expect. All right, now getting to the error correction. So another important results that we had last year was the release of this quantum LDPC code that we are planning to use to implement our error correction. And so for now, this is a quantum memory of the paper, and so the main result of that paper is that we drastically reduce the number of qubits that you need physical qubits that you need to implement logical qubits. So the overhead is drastically reduced. If you look at like surface codes, for example, you would think about 1,000 to 3,000 qubits. But for these codes, I think we're able to reduce it to like something around 240 or between 200 and 300 physical qubits or logical qubit. So that's really good, but it does require us to implement new couplers or new connectivities on the chip. So if you're trying to like look into the future a little bit, these are the types of connectivity that we'll need to implement in our architecture in order to make it happen. So we need three types of couplers. We need these C couplers. They're called C because they're roughly 1 centimeter long. So these are going to be on-chip couplers, which are going to go up, across, and then down. So into the third dimension, and we are going to be able to connect distant qubits like that. And the goal is to do a degree 6 connectivity coupler, and I'll show you that after. We also need the M coupler. So that's if you take 2 chips and you bring them kind of very close, we can build these little bridges so that you will be able to do entangling gates between different qubits on the neighboring chips. And also we need the L couplers. So you can think of that being living in kind of one canister inside the fridge, that be living in another canister inside the fridge. And then we want to connect these two via a quantum link. And so we've also had that. That's exactly it. So if say within a single fridge, you can have these, these rack of like 3 sets of chips, and then you want these bridges between both. They're basically coax cables of around 1 meter long that connect the chips. And so we've also have that in the lab right now.
So you've got entanglement between 2 different refrigerators, 2 different.
So it's one fridge, but 2 different kind of payloads.
Okay, but not two separate refrigerators.
No, that's today.
Oh, that's going to come.
Yes. So little C coupler. So remember the on-chip 3D coupler. We're able to do a degree 6 connectivity with superconducting qubits, which is quite a challenge if you have a superconducting qubit community. But we're able to do that with 10⁻³ error rates between all the qubits. So that gives us a confidence that we're taking the right steps toward implementing these LDPC codes. And so kind of the grand vision again that loops back to the the quantum centric supercomputer. So I think last year we signed a big partnership with Chicago and Tokyo to basically design what a 100,000 qubit system would look like. And kind of the grand vision that we have in mind is to have all these fridges together, and these are called the IBM Quantum System 2. So we can have different clusters of fridges connected together via the couplers that I showed you. And then we need all these classical and quantum connections that are connecting the different fridges. And so we need all these transducers and optical components to make that happen. Not today, but it's coming eventually. And that gives us like a little bit less than a decade. So we're on it.
Are the actual physical internet connects going to be at the millikelvins as well? How are you going to avoid noise?
So we are transducing, so we can go. That means that we might go to optical.
Sorry,
So we might go to optical if we're transducing. Okay. So I don't think the connections need necessarily to be called. That yeah. So in summary, if you look at kind of the hardware that's coming up online in the next few years, there's a few things to be on the lookout for, as the number of operations increases. So you can say that in 2024, we enter what we call the era of quantum utility with this groundbreaking paper. And then in 2029, there's going to be a new era where we're going to have like error-corrected computers. And so one thing I want to point out is, as you increase the number of operations that you can do in your circuits, it's going to be increasingly more difficult to simulate these circuits. So because there's going to be more and more operation that you need to take care of. So if we look at like the different error rates that we're going to have, so these error rates are given by these like gamma parameters. And that's what dictates how many operations you can do. So you have a lower error rate, you can do more. And you're trying to look at what is the crossover in terms of computational costs to simulate the circuit classically. Realize that right now, maybe in 2023, using a bunch of these NVIDIA GPUs, the crossover is around 46 qubits. But by 2026, because error rates are increasing, this crossover point is dropping down to 32 qubits. So kind of our narrative here is that we don't necessarily see long-term value into CPU or GPU simulations of quantum circuits. Even if they can compete today, we see that that competition kind of going away in the pretty soon in the future. Okay. Question on that before I switch gear again. Awesome. Yes. So. Okay, so yeah, we can go on, forever building new hardware. But as mentioned before, a quantum computer is just a paperweight if we don't have performant classical software. So we need this very performant stuff on top of it. And kind of the way that we like to see it is that you take Qiskit, which is our quantum SDK to control the to program the quantum computers, plus the QPUs. So you need actual hardware, and that gives you that gives you work, right? Or that's how you do research for quantum. Yeah, and so are you familiar with Qiskit? Just show a hand. Okay, so yeah, so for those who don't know, so Qiskit, as I said, it's all coded in Python. That's our SDK that helps you program the quantum computers, and it's everything that helps you like take a problem, map it to a quantum circuit, optimize your quantum circuit to eventually run it on the hardware. And there's a lot of like post-processing tools that are also included in Qiskit, all coded in Python. And kind of at a high level, the way to look at things is if you have like the systems that's actual hardware that you look at that you use, and then on top of that you have the Qiskit runtime. So Qiskit runtime is actually some hardware, classical hardware that lives next to the quantum computer, and that is what basically samples the quantum computer, sends the jobs to the quantum computer. And then on top of that, I'll talk about the Qiskit functions later. These are like package code. And then on top of that, you have like Qiskit, and that's how you program the quantum computer. And we have all these kind of fancy AI tools that kind of are adjacent to it. I have the Transpiler service, so that's I'll talk a little bit about it later, but that's an AI tool that helps you take the circuit that you're giving to Qiskit, and then it just transpiles it to something that the machine can run. And with the use of AI, we can do that more efficiently. And now we have a little Qiskit code assistant as well that's built on Watson-X, which is our IBM's version of the large language models that helps you program Qiskit. So you can have a try at that. Okay, so I'll skip that for now. But yeah, just to kind of give a little bit of motivation. So I think the motivation is clear by now. Like we do need fast classical software. Just the result that I showed earlier with the utility experiment, where remember there was only like 5 minutes on QPU. So we do need to speed that up. And one thing that we did is we translated a lot of the libraries behind Qiskit into Rust, which is a very fast compile language model, programming language. So that sped up a lot of the operations behind Qiskit. And so I think now with all these improvements, if we're trying to like compare to other SDKs, we came up with this series of tests that we call the bench press, and they're all open source. You can have a look. And this basically looks at how many compares the different programming languages on the different tests. So like if you're transpiling, how many 2-qubit gates you end up having, to how long it took to get to that circuit, and things like that. And Qiskit basically was the best for most of these tests, and the closest competitor was Ticket, and but even there was quite a big margin in the performance. So like we can have like 53% fewer 2-qubit gate and like almost 30 times faster. So Qiskit is becoming really, really fast to control quantum computer. But on top of that, so classical software, or like fast classical software is definitely necessary, but it's not sufficient. It might be sufficient for some people, but not for all. And so if we think again about this, Qiskit plus QPU equal work, then we want to add another layer on top of that, and that's what we call the quantum software. So these are like prepackaged code that will speak to different audience than quantum physicists. Because Qiskit was good to talk to these people before, and that's what we claim is going to unlock the useful work. So it goes from research for quantum to research with quantum. And so what are these? So that's kind of the way we're thinking about it. At first we had Qiskit, and that spoke to the quantum physicists, like me, Nick, and a bunch of people here. But what if we want to talk to like quantum computational scientists? So these are people that want to program quantum computers, but don't necessarily want to care about the details of the intricate details of the hardware and the error mitigation that they need to use and kind of the details of this error mitigation protocols. So what do we have for them? So we just announced the launch of Qiskit, what we call Qiskit add-ons. So these are tools that will help you in the workflow. So the way we think about a workflow in quantum computing is you have kind of these four steps. First, you need to map your problem to a quantum circuit, and then you need to optimize this quantum circuit, transpile it and make sure that it fits well into the hardware. And then, of course, you need to execute on the hardware. And eventually, you might want to like post-process, and that includes error mitigation and trying to get relevant information out of the outcomes of the quantum circuits. And so we launched these three Qiskit add-ons for now. One is a multi-product formula, which helps you get better results with the Trotterized circuit. One is the operator backpropagation, which is basically a way to reduce the size of the depth of your circuit at the cost of running more circuits. And then we have SQD, so that's the sampling-based quantum diagonalization, and that's the procedure that we use in the quantum chemistry paper I talked about earlier. So that's now all available on Qiskit, and you should have a look. And then there's another class of people, and these are the scientists. So eventually, the scientists, they don't necessarily care about quantum algorithms or quantum programming. All they want to do is to use quantum computers. So they have a problem in their head, and the problem would require to be solved by a quantum computer. So what tools do we have for these? So we just launched the Qiskit functions. So this is, again, building layers of abstraction on top of Qiskit, on top of Qiskit add-ons. And we have, so that's kind of like these big boxes that encapsulate all of these steps or automate all of these steps. We have two types of functions. One is applications function. So that's really if you come with a problem, you just enter it into the function and then it gives you an answer at the end. Or circuit function, which basically you will still have to do the mapping of the problem, but it encapsulates a lot of error mitigation and optimization methods on it there. And we're not doing this alone. So actually, most of these functions, they are being built by some startups that are partners of IBM. So some of them you might know, like Q-Control, Qnasys, Algorithmic, and Kedma. So they all build these prepackaged Qiskit code and they offer it on the functions tab of the quantum platform of IBM. There's one by IBM, and that's the AI transpiler that I mentioned. So that is available for free for all the members of the IBM Quantum network.
So just to finish.
Yeah, I'm pretty much done. So like we unlocked that. So yeah, so maybe what I'll say, I can basically wrap up here and just go here. So kind of the way we see this is, there are two ways to get to a quantum advantage faster. Like we're not yet at the stage of quantum advantage, but basically we are going to keep building better hardware and better software and making it available. But we also need algorithmic advances, and for that we cannot do it. We cannot do it alone. Like we cannot be doing all the hardware, but also all the end user application and understand all the problems of the different industries or the different fields. So we really need the help of our network of partners to find out what useful stuff can we do using this hardware. So like the hardware is going to push the capabilities of quantum, and then you'll have like algorithmic advances that will kind of lower the resource estimations for running certain application. And here there's just a famous there's a recent example of Shor's algorithm being drastically reduced by using like parallel quantum circuits execution. And so to wrap up again, the reason why we're here is because we have this quantum computer in Quebec, and it's actually like that very one there. So if you do want to see it, it's like not too far from Montreal. So like reach out to us, we can take you there. It's really cool, very fancy, very shiny. Currently, it's an Eagle R3 chip that lives in there, so we have a 127 qubit. It's actually one of the best Eagle chips that we've done. But we plan to upgrade it to a Heron sometime next year. And yeah, so there's a way for you to get access if you do want to run some algorithms on it. So you can talk to Dvira and Anna Dyring as well, so they can connect with us easily. And yeah, and also like you're not alone. Like we have some enablement programs as well that a lot of like self-paced education, but that goes all the way to like hand holding to make sure that your circuits can run very well at scale on the quantum computers. Because like you'll realize if you're trying to run things at 100 qubit, then you run into some scaling challenges. And so we know a few tips and tricks that can help you. Yeah, so I think with that, I'll stop here and take questions.
Thank you very much. Yeah, that was beautiful. Going all around. Yeah.
Thanks for keeping me engaged as well.
So we've had quite a few questions during the talk, so thank you very much. I think we want to ask after. That's and we will host you again, I'm sure, right?
Oh, yeah.
Especially for the Quantum Software Consortium.
Yes.
Yeah.
Yeah.
Oh, how do we get them? Anyone on this?
Oh, there's one. No, it's fine.
Yes,
There's none.
okay.
You didn't see it?
Awesome. Yeah. So
Okay,
we're here
thank
if
you
you want
very
to have a
much.
chat. Thank you so much.